Welcome to another ORAC video. Intermediate one this time. We're looking at Medusa snakes from 2019. I remember it well. So you have to read the question yourself. We have the DNA of a snake, and if you can get 3 S's in a row and 3 A's in a row, 3 A's, 3 K's, 3 E's in a row, then that means it will have a venom level of 3. But if typically a snake's DNA will be sort of mixed up, and you'd need to remove some so that you're able to get the 2, the answer here is 2, because you can get an S there and an S there, followed by N, and then A, K, K, and E, but you can't do any better. Okay, so there are subtasks, and that's going to be the first thing we look at here. So subtask 1, all the S come before all the N, which come before all the A, which come before all the K, which come before all the E. So sample 2 is an example of that. And so if you can solve that case specifically, then you can get 15 marks. And that's very easy to solve, because here we've got, say, 4 S's. Well, actually, I can switch to a whiteboard here with that data in it. So here we've got 4 S's and 3 N's and 4 A's and 4 K's and what's that, 7 E's. And so the minimum is 3, and that's the answer, because we can have our 3 S's, 3 N's, 3 A's, 3 K's, and 3 E's. It's no point trying to do any better than that, because the N is the bottleneck. All right, so we can solve that one very easily. So I'll switch over to the code, and here we've got that data in test 1. So I've set up my input and output and in and out close. I'm reading. You can see that the data, you've got to read a number followed by a word on the next line. So my code is reading the number N, which I'm not going to use. I have no need for it. And then data is on the next line. I've put all this inside a function called ORAC, and then I'm calling ORAC. And I've got an answer of 5 just to have an answer, and I'm printing it. And if I run it, then it just runs, and whatever. I suppose I should print the answer to the screen as well. Okay, and run it, and there we go, 5. Okay, so now let's do some actual work. So we're going to look at subtask 1, and I'm going to put that in a function called subtask 1. And you'd need to pass it some data, and you've got to get the answer from that data. Okay, so we need to count the S's, count the N's, count the A's, and so on. But what we can do, we can just take a general approach to that and say we'll get a tally. All right, so I'm going to say T equals tally the data. Tally doesn't exist. I think there's a library you can use in Python to write, but I'm going to write it here. It's good for you to see. Right, so tally, we're going to have just a whole bunch of values, which I'll call X's, and I'm going to say answer equals an empty dictionary, and for X in X's, I'm going to tally that in the dictionary. So I'm going to say answer X. Well, I'll say if X not in answer, then we're going to say answer X equals 0. And now I'm going to say answer X plus equals 1. So that's just going to count how many of each thing is in there, right? And then we'll return the answer. So let's have a look at that. So let's go. Well, I'm just going to run. So now everything's defined, and so I can say tally test 1, and there you go. It tells you there are 4 S's 3 N's, 4 A's, 4 K's, and 7 E's. And then we just want the minimum of those. So basically I've just got to take the minimum of the, now, good. I've never mentioned this before, but when you do a calculation here, then you can get the previous answer by just doing underscore. And I can do that again. So now I'm just going to say the minimum of the previous answer dot values. And that'll be 3, and that'll be our answer. Okay, so subtask 1, I'm just going to return the minimum of the tally values. Okay, and so I can now say answer equals subtask 1, passing it the data. And yeah, I can go run, and so it goes 6, all right? And here's my data, and that's not going to be the correct answer for this because it's not following the correct format, like all the S's and all the N's and so on. But I'm now going to submit this, and let's see what happens. So I'm really making a point for you that you can concentrate on subtasks if you want. So getting lots of wrong answers, but look, subtask 1, we got all correct. And so we've got 15 marks. So we've now got we've got 15 out of 100. And now, if I go on to solve subtask 2, which I'm not going to do, I spent a bit of time working out how to do subtask 2 by itself, and I just decided it's not worth the time in the video, but you can have a think about it if you like. So subtask 2, it's got snake repeated some number of times, like this one for example, and yeah, so I'm now just going to concentrate on a general solution. But in the AIO, if you solve subtask 1 like I just did, and you get that 15 marks, that 15 marks will never be taken from you. So you can now delete your subtask 1 code or comment it out, and you can now concentrate on code for a different subtask. And when you run it, subtask 1 might be all wrong, but you will not lose the 15 marks that you gained. Now that's not true on ORAC, but it's true on the AIO system. Anyway, I generally don't like to focus on subtasks. I like to think of a general solution, but if a problem is very challenging, then working on individual subtasks can be both a way of getting some marks and also a way of just working on a smaller problem, hoping to get some insight for the larger problem. So subtask 3 means that you're dealing with at most 10 letters. So the answer could only ever be 0, 1, or 2. And maybe you can work that out somehow. And then subtask 4, N will be, you'll have at most 1,000 letters. And in subtask 5, you'll have at most 100,000 letters. So just 3, 4, and 5 is just your data is getting bigger. And if you have a slow algorithm, then you might be fine for subtask 3 and maybe subtask 4. But a slow algorithm, you'll run out of time to answer with a very large data set. Okay, so let's get into a general look at this then, and that would be by taking a look at some data that I crafted, and let's just have a general discussion about this. So we can see that there are S's scattered throughout there, and just at a human level, like we'd probably take those 2 S's and like maybe that one, but how can we know? How can we know whether if we take the 3 S's, then we're gonna have to now get some N's, right? Well, it's we're gonna run out of room, aren't we? Now A's, yeah, we can't do 3, right? Maybe we could do, I don't know, something like get the index of all the S's, S is index like 0, 1, 3, and then whatever this one is, maybe that's like 14 or something, and then 16, and then maybe 25 or whatever that happens to be. I don't know if that would help. Maybe there's a dynamic programming approach. Dynamic programming is where you say, what if that was my only data? Then the answer would be 0. Okay, and what if that was my only data? Well, the answer would still be 0. What if I had this? Well, maybe I could record that at least I've got an SN, you know? And the point of dynamic programming is that if you say I look at this, right, and I know I've got an SN, right, well then when I look at this and the current character is A, if I've recorded that I've already got an SN, then that goes well with the A. The point is you remember previous results so that you don't have to recalculate things all the time. Okay, so maybe there's a dynamic programming approach to this problem, but I've never found one, and I'm not going to explore that. So what I'm going to explore now is simply the idea that I'm going to have a function. When I'm exploring an informatics problem, I just imagine there's a function called f that tells me what I want to know. And if I say data and I say 1, then that's going to tell me true or false according to whether we can get an answer of 1. So we surely can here. So like S, N, A, K, E, yep, we can get an answer of 1, so that's true. Right, can we get an answer of 2? So I'll rub out that working. And we'll go S, S, N, N, A, K, K, E, E. So yes, we can get an answer of 2. Can we possibly get an answer of 3? And so this is maybe where dynamic programming could possibly come in if, you know, I don't want to overthink it, but I'm doing a lot of repeated, you know, looking at the list here. So S, 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 N, 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 A, K, 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 and E, E, E. So yes, I can get an answer of 3. Okay, we're getting pretty close to the end of the DNA there. So I'm not all that hopeful that I can get an answer of 4. But let's try S, 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 and then N, N. Now that's not looking good, is it? N, N, and then, so this is definitely false. And so the answer is 3, right? So if I start at if I start at 1 and go up, well then as soon as I hit a false, I know what the answer is. I know that the answer is 3. So I'm going to concentrate on this approach. So what would that mean algorithmically? So how would I define this f? So I need some data and I need a number n to say how many things I'm looking for. And basically I need to start my search at the 0 index, and I'm going then I need to like find n lots of s and get to position j, right? So in this case, like if I say, let's make it like 3, because that's the actually I'll redo this for I'll redo it for say 2. SS, no, I'll redo it for 3. S, 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 N, 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 A, K, 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 E, E, E. And I need some indices here. Wish I'd written them in before the video. So let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Okay. I'll just rewrite that 20 so it's on the screen. Okay, good. Now, so I need to find 3 lots of S starting at position I. Okay, and so that takes me up to position 3, right? So that this number here will tell me what the third, right? And so now I'm going to say I equals that 3 plus 1. Okay, so I'm going to start now. I'm now going to start at the 4. So I'm going to find 3 lots of n start at I. So I'm starting at position 4, right? Now that's an A, but here I get the n, and n, which takes me up to position 9. And then I'm going to just move on 1, and then I'm going to find 3 lots of A starting at position, that's at position 10, right? That's position 10. So I'm now here, and my A takes me up to position 14, and so on, right? So if I can complete this for S, N, A, K, and E, and not run out of string, right? If I can find my final E before I run out of string, then the answer to this will be true. If I do run out of string, then the answer will be false. Okay, so let's get into this. All right, so I'm going to get rid of subtask 1, and I don't need a tally, but you might like to write that code down as a bit of useful code you could use in the future. Okay, so I'm going to say def solve. And all right, so another name for my F would be def is solution data n. Okay, and so this returns true or false. Okay, and solve, just give it the data and say return maximum level of venom we can get in this DNA. Okay, so that's and so the has solution is our F that we worked out. Let's write solve. So I'm going to say n equals 1. We're hoping that that we can at least get 1. I'm going to say while true, give me an infinite loop. I'm going to say if not is solution, the DNA with the number n. So if we can't find a solution, then we're going to return n minus 1. Right. So if we can't find a solution for 1, then the answer is 0. If we can do it for 1, 2, 3, and 4, but then we can't do it for 5, then we'll return 5 minus 1, which is 4. Okay, so I'm going to increase n by 1. Maybe I'll put that in else. Okay, else n plus equals 1. So n will just keep creeping up, and then when we can't find a solution anymore, we get out of this loop and in fact get out of the function. So that's the idea, but now of course we need to write this has solution. Now before I do that, so I've got this test 1 and I've got test 2. Let's look at test 2. I'm going to say t equals test 2, just so I can just write t. Now Python has, so t is a string. If I go type of t, it's a string. A string of letters put together. That's the reason for the name string. in Python, a string has a method called index, where I can say, give me the index of, like the first index of k, for instance, and that's at position 6. So 0, 1, 2, 3, 4, 5, 6, right? It found that one. But I can actually say, no, I don't mean that k. I want you to start at position 20 and find the next k after that. Oh, that's good. Now, we also, just looking at my page, we also have one at 29, right? And it'll find that. But if I go to 30, there are no more, and I actually get an error. Okay, I'll get a value error. So I can use this. I can use this quite nicely, this index thing. Okay, so can we find n times s, then n times capital N, etc. Before we run out of string. Right, now, this comment has gone over 2 lines, so I actually need triple quotes. That's the multi-line string, so that's a comment for the function. Okay, so I'm going to start by saying position is equal to 0, and I'm going to, well, how about it? So I don't want to write code where I write it for S, then write it for N, then write it for A, then write it for K, then write it for E. I want to write a loop that handles all of those. So I'm going to say for letter in SNAKE. That will, just in case you don't know, that will just print each letter one at a time. Okay, just so is solution. I'm going to we want to test this. So print is solution. I'll give it test2, and we'll just start with 1. Oops. Okay, and then I'm just going to maybe, I won't exit, but I'm going to not run the ORAC stuff, okay, because I'm in testing mode here. So if I run this, okay, then I get an error because I forgot to close that quote, and I run this. Okay, so there we go. For letter in snake, print letter, we get SNAKE, and then this function doesn't return anything, so the return value is none, and that's why that printed there, because we've printed the return value and it's none. Okay, if I did return 7, then that would give us a 7, but this is meant to return true or false, so there you go. All right. Right, what are we going to do with it? Well, say the letter is S, right? So now I have to look for, so I have to go data.index, so I'm looking for the letter starting at pos, right? And then I need to collect that in a I need to collect that, so I could say I for index equals that, and then I want to move the position on. So the position is, so then the next time I go looking, then I move then I move along one. Okay, but this is only doing that once, and I need to do it n times. Well, I know how to do something n times. I do this for underscore in range 0 to n. Okay, that will just do something n times. I don't need to use the number n, right? So I just need to do it n times. Okay, so this will find, you know, 1 S and then 2 S's and then 3 S's, right? And then once it's found 3 S's, then it'll find 1 N and then 2 N's and then 3 N's. Okay, and then if we can do all of this and not run out of data, then we can return true. Okay, we're only returning true or false here. Okay, so now let's see, when I run this, what it'll tell us is solution test 2 1. Okay, n is not defined. That's because I need a small n there. Right, that's the one that was passed in, not a capital N. Okay, true. All right, can I get a solution of 2 out of this? True. Can I get a solution of 3? Should be true. Can I get a solution of 4? Should be false. But it says error. Can I get a solution of 5? Oh. Okay, curious. Okay, right. So now I see my pos is just going up by 1. The pos is meant to be I plus 1. Okay, that I was just a temporary variable. Okay, so now, these tests weren't very good. Let's just go back to say 2. Okay, that's true. Let's try 3. Oops, wrong button. Okay, true. Let's try 4. All right, and we get an error. Now, I knew we were going to get an error, but you didn't. So we've got a value error, substring not found. Okay, and that's because we're calling this data index, and we have run out of string. And when you run out of string, you get an error. Now, what we can do here is, what we will do, Python allows you to, if you know that an error could occur, and we know that an error could occur, then you can sort of tell it to be careful, right? So the try means try all this code, but if an error occurs, then okay, I'm going to do this, and now, just to show you, if it's a value like 3, we get true. If I change it to 4, then we'll get error occurred and we've exited. Okay, now I don't want to print error occurred and exit. All I need to do is say return false. That's what this function should do. It should just return true or false. Catching the error is just how it works. Okay, so now I get false. All right, beautiful. So just to see that, I'm just going to say for n in range 1 to 7, I'm going to print n and is solution, and there we go. All right, true, 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 false, false, false. Right, and so now we should be able to run solve on this pretty easily. Okay, I'll get rid of that. We can literally just go solve test 2 and get an answer of 3. And we can go solve test 1 while we're at it and get an answer of 3. Okay, that test 1 was solved by subtask 1, but now this is a general solution. And so, yeah. So this was really interesting to me when I first encountered this problem 5 years ago. Spent a lot of time trying to solve the problem directly, as in like calculate the best solution. But what you need to do instead is just ask it questions. Say, can you find a solution of 1? Can you find a solution of 2? Can you find a solution of 3? So now let's see if this lights up all green. Sure, hope so. Just check that I've saved the file. I'm sure when you run it, no, it's not saved, but when you run it, it saves. Oh, and I need to actually call the ORAC stuff now. So let me just check that. Okay. Right, get rid of subtask 1 and call it solve. Okay, and so that's got it. Right, that's actually the same data that we've been working on. So this is ready to submit now. It's not doing anything extraneous and it's doing everything that it should do. Good. Okay, let's submit. hope for the best. Right, now we've got some blue, we've got some green, we've got lots of green here. We've got some blue. Now that says time limit exceeded. All right. So it's not giving a wrong answer, but it's running out of time. There are time limits on how long your code can run for. Okay. Right. So now this is interesting, right? I've solved subtasks 3 and 4, which I'm sure you'd remember are the ones where n is fairly small, less than or equal to 10 and less than or equal to 1,000. But the ones that are very large, and you can have large n in here, it's just that you've got the very predictable format that you can exploit. So you can have large n in here as well. So when n is large, my code is failing. Well, sorry, not the code's failing, but it's failing to produce the answer quick enough, and it's being cut off. All right, now I knew that was going to happen, but you didn't. And so this was so appealing, wasn't it? And luckily, like, this approach is not being thrown out. So we have code that will determine whether a certain solution is possible. The problem is we're trying too many of them, right? So if there were 100,000 characters in the input, then the maximum possible solution is 20,000. And so we're asking, can you do one solution? Can you do two? Can you do three? Can you do four? Like, you're doing it a lot. And every time you ask it, does it have a solution? You're basically potentially doing a run through the entire data. So we're doing potentially thousands of runs through the entire data, and each run through the data is accessing, many thousands of characters. So that's multiplying to give many millions of little things that we're having to do, and that's why it's taking too long. So what we're going to do, I'll just switch back to pen and paper. What we're going to do is something called binary search. So step aside from this problem for a minute. If I played a guessing game with some children, said I'm thinking of a number between 1 and 100, and let's say I'm thinking of the number 72, right? Oh, sorry, you can't see that. All right, there we go. Right, so I'm thinking of a number between 1 and 100, and in my mind I'm thinking of 72. And I'm going to say higher, lower, or you got it. And so, children might say, 20, and I'll say higher. And they might say 30, and I'll say higher. 40, higher. 50, higher. 60, higher. 70, higher. 80, lower. And then they might go, 79. You get the idea. This could be very inefficient, right? So that's a bad strategy, is just to guess whatever number comes to mind, and then make small changes. A good strategy is to start in the middle, say 50, and I'll say higher. And then, right, so now let me just make some notes. So we know that it's somewhere in 1 to 100. So if you guess 50 and I say higher, well, now you know it's in 51 to 100. And so let's get the middle of that and say 75. And I say lower, so now we know it's in 51 to 74. And let's get the middle of that, right? So that's about 60, 67. And I say higher. So now we know it's in 68 to 74. And so you get the middle of that, which would be 71, and I say higher. So we've narrowed it down to 72 to 74, and the middle of that is 73, and I say lower. And then, so what have we narrowed it down to? Lower than 74, So it now could be 72 or 73. Okay, there's no particular middle of that, so you're just going to, guess one of the two, and then, yep. All right, so we would have got it in either that guess or the next. So basically, if you use this approach called binary search, binary just means you've got two options, and so a binary search is where you narrow things down basically by half every time. Then in a 1 to 100 guessing game, you are absolutely guaranteed to get the correct answer in a small number of guesses, right? So basically 2 to the power of the number of guesses is the search space that you're covering, and 2 to the 7 is 128. So that means that if I said I'm thinking of a number between 1 and 128, that means 7 guesses will definitely be enough to get it. So for 1 to 100, 6 or 7 guesses is guaranteed to be able to get it. So we're going to do that thing here, okay? So the maximum length is 100,000, and so that means the maximum possible answer would be 20,000, right? So we could start by saying the maximum possible answer is n, double divided by 5 plus 1, just in case we've truncated too much. Okay, now let's say the input comes in. Let's say the n happens to be, 5,000, right? Then that means that this is going to be 1,001. And so we know that it's going to be somewhere between 0 and 1,001. I've included 0 this time because 0 is a legitimate answer. I suppose maybe a strategy might be that we check for 1. We check 1 first, and if there's not 1, then we can answer 0 quickly and not bother doing any binary search. Okay, so we'll do 1 to 1,001. And so we will call, so I'm just going to use f data, comma, we'll call the middle, let's just say 500, right? And if that is false, then there's no point trying anything higher. And so we've narrowed it down to 1 to 499 in this case. And so if we take the middle of that and we call f data 250, right? And if that happens to be true, then we've now narrowed it to 250 to 499, right? And so we keep going the middle of what we've got. Now, I'm going to suggest that if we get it down to a window, so this was a window of about 1,000. This was a window of about 500. Then we've got a window of about 250. If you can get it down to a window of about 5, well, then you could just try each one of them, right? Rather than trying to narrow it further. At worst, you're going to do a few more searches than you need to, but you're still overall doing a fairly small number of searches. Okay, so implementing this can be a bit tricky. I'd probably rather have a go with pen and paper before I use the computer, but the video is already very long, so I'm just going to hope that I don't make any mistakes, right? So I'm going to call this solve linear and then do another function called def solve binary search. Well, I'll just call it solve binary because that should be called solve linear search. So this is a solve binary search. Okay. And I'll put the same comment in. Okay, and I'm going to say the maximum answer. So we're going to say max equals the length of the DNA double divided 5, and I'm just going to add 1 just as a precaution. And okay, so that looks a bit weird having the, I just don't know what to call it. I'm just going to call it M, right? And I'll put a comment. M equals maximum possible answer. Now, suppose I said we were going to do a search of 1 first, right? So I'm going to say if has solution DNA comma 1, or if not has solution that, then we're going to return 0 and then not bother with any of this. Okay, and now, so I'm going to have a window that can be, we'll call it L and R. So L equals 1 and R equals the max. Actually, I don't need a letter for M. I can just use this. Okay, and we're just going to change L and R in response to what happens, right? And I'm going to say window equals L minus R plus 1. So if your window went from 6 to 10, that's actually a window size of 5 because it's 6, 7, 8, 9, and 10, not a window size of 4. I'm just going to calculate the window just because I feel like it's a nice thing to do. So now what? Well, we're going to need a loop, aren't we? And I don't have any obvious condition for exiting the loop yet, so I'm just going to make it infinite. All right, so what do I do? Well, I guess I'll get the mid equals the L plus R double divide 2. Okay, hoping that is that's good. And so now I'm going to say if now I called it has solution here. I mean is solution. So I've got that function up here. If is solution DNA comma mid. Right, so if I know that it's between 1 and 1001, then I'm now asking about 500. So if that is a solution, then I'm going to put a comment. Our answer is in the upper half. And so that means I'm going to change the L. And so I'm not going to try mid again, so I'm going to do mid plus 1. Okay. And then else, I'm not going to call has solution again, but now we know our answer is in the lower half. So I'm going to change the R. And so that's mid, not mid, R equals, mid minus 1. Okay, now I've got to be careful here. So if I have mid plus 1 and mid minus 1, then it means I'm locking mid out forevermore. I feel a bit dodgy about that. So this is the happy case where it was a solution. I think I'm going to just keep mid in the game there. And if it wasn't a solution, then there's no point ever thinking about that mid again. Okay, I'm going to update my window, which I haven't used yet. And now, I suppose I want to just keep doing this until I get a window that's, say, less than 5. So I can actually put that in my while condition. While window is greater than 5. All right. So that'll just narrow things down nicely. And I think I'm going to print No, I won't print anything. Not yet. All right, and then when it's done, when it's got a window as small, like a reasonably small window, then I'm just going to do a linear search on what remains. So I'm going to say for n in range, and I'm going to start with L and go to R plus 1, I guess. And I'm going to say if not is solution, DNA comma n, then return n minus 1. That's the sort of logic I had before. So we don't return anything here, we're just narrowing the window down, and then when we have a small window, just do a linear search on that, and that's where we do a return. Okay, I'm not super confident this is going to work because it's moderately complex code, but we can give it a go. Just trying to work out what's the best way to give it a go, because you really kind of need large data to really exercise it. But I might just, right, so that's solve, which I don't have a solve anymore, so I'll say solve binary. So I guess I can just, I don't know, run it and see. Doesn't hurt, does it? Right, run. Yep, gave me answer of 3. I did run it. Oh well, I'll put it in ORAC and we'll see what happens. I might get some wrong answers, but I probably won't get any timeouts. Nervous wait for it to get started. Oh, I do have a timeout. I wonder if it's fewer timeouts than before. I can probably look. It remembers all of your submissions and you can look at the details. So I'll have a quick look, just eyeball that and go to my own profile and go to submissions. And here we've got our Medusa snakes. I think I must have pressed the wrong thing. Here we go, press that one instead. Okay, so this one was strict. No, I think it's actually the same pattern of timeouts. Okay, so that's surprising because doing the binary search cuts the work down by a huge amount for a long string. All right, now I do have one more trick up my sleeve, but I acknowledge that the video is long already, but I'll just go on. Don't have to watch it if you don't want to. So the problem is we're running this is solution. We're running it quite a lot, and every time we run it, we're doing a potentially long, we're doing a potentially full pass through a potentially long data set. So what we could do, and I don't think I actually will try to implement this. I think I'll just try to demonstrate it. So I'll do that with pen and paper. Right, so what we can do, oops. Just clearing up a bit. Okay, we can build a bit of a table. That is a dictionary, all right? And so we'll have our letter and we'll have the indices. Now, S, and now this is going to take a bit of time to write out, but S has indices 0, 1, 3, 10, 12, 18, and 33. N has indices 2, 5, 7, 9, 16, 20, 31, and 32. A has, now a thought's just occurred to me, but I'll save that. So A has 4, and 11, and 13, and 14, and 21, 27, and that's it. And K is at 6, and 17, 19, 22, 24, 25, and 29. And E is at 8, 15, 23, 26, 28, 30, 34. Okay, hope I got everything. Now what occurred to me, here's our smallest number of letters, which we could easily get in a tally, and that can give us an upper bound on the answer. Right, so we can actually cut down some work, because instead if we've got 20,000 letters come in, then that would mean that our maximum is 4,000. But if there's only 13 A's in there, then that means that our maximum would actually be 13. That would be worth coding, but that would, I guarantee that would not be enough for us to pass, because they'll have some test cases where the data is very balanced. Okay, they think of everything. Okay, now, if we pre-process this so that we know where all the indices are, instead of like looking through the list every time, then we can be a bit smarter. So what would F data, 3 look like this time? Well, we'd start at 0. We'd start at 0, and then we'd look at, I'm just going to call this T for table. We'd look at TS, right? And then we'd take the first 3, because we only want 3 of them. That gives us 0, 1, and 3. That means we're now up to index 3. And so now we want to start looking at index 4, and we'll take T of N. Now that has 2, 5, 7, 9, 16, and some more, but we want to start looking at 4. So forget that. Yep, we'll take that one, and that one. Thank you. So we're not looking at like every single one of these letters. We're just looking at a summary. You know, we've got the relevant information. So we're up to 9, increase by 1, and start looking for A's. Now, A's, like there's 4, 11, 13, 14, 21, 27. We're not interested in 4 because we've got to start at 9. So we'll take 11, 13, and 14. Okay, so now we're up to 15. And we'll look for K's. And we can go 6, 17, 19, 22, 24, and so on. We're not interested in 6 but we will take 17, 19 and 22. And so we're up to 22, add 1, 23, and finally we look at E. That's right, so 8, 15, 23, 26, 28, 30, 34. We're not interested in the 8 because we're starting at 23, not interested in the 15, but we'll take the 23, 26 and 28, and so because we didn't run out, then the answer is true. Okay, so that is less work than repeatedly going all the way through all of these. Problem is, if the data is, if the data is literally 100,000, then each one of these, could be around 20,000. And if we're asking, is there a solution that's, say, 17,000 long, then that means we'd be skipping an awful lot of these before we start counting. And so we'd probably still time out, because this would reduce the work, but it probably wouldn't reduce it enough. But what we can do is actually do a binary search on this. So if I can just undo some crossing out here. Okay, so we're going to start at position 23, and we have these indices. What we want to know is, where can I find 23 in this list? Or a number, let's say I wanted to start at, at 21, sake of argument. There is no 21 in the list, but I want to find the smallest value that's greater than 21 in this list. Well, can do that with a binary search because this data is sorted. Oops. Okay, because this data is sorted, we can do it with a binary search. We can say, pick the middle of the list, that's 26. Well, we're looking for a number smaller than that, so we've narrowed it down to this. Okay, pick the middle of that, 15. Okay, right, well, we're looking for a number higher than 15. Take that. Okay, well, we're looking for a number lower than that, but we know that the window's closed, and so this has to be the one that we're after. Okay, so a binary search on this index list will be enough to cut the time down and solve the problem. And I know that's the case because I've solved this problem before, and that's how I did it. Okay, so I'm not going to write that code now. I just think it'll be fiddly, and so I'll leave that as an exercise for you. But let's see. Do I have a... No, there's no Medusa snakes in here. But if we look at the problems and scroll down, 2019, okay, I've got a score of 100 for that. Right, so it somehow knows that I've done it in the past, but it doesn't have a direct record of it. Last thing before I end the video, we'll just have a look at the Hall of Fame. Okay, and narrow it down to Python and just choose. Okay, so has snake n DNA length, so you can see that's the same sort of approach that's being done, although the code actually looks quite different, and I'm a bit worried that this looks quite inefficient, but that's curious. And then here we have the binary search approach. So I was trying to avoid it, but this person's done that binary search in 6 lines. Okay, so it gives you some hope that you could do it. There you go. They've got all their greens, right? Another one at random. Okay, you can see there's a binary search there. Yep. Okay, here we go. Here's my code that you didn't see this time. Okay, so I'll leave this up in, I'll leave this on the screen. You might want to pause and take a closer look. Scroll down for you to pause and take a closer look if you wish. And yeah, and that's all we've got. See you later.